In lesson 3, you'll learn how to represent forces in situations where the system is in equilibrium, when the resultant force is 0 in both the y direction and the x direction overall. But what if it isn't? What if you have, at least in one of the directions, a resultant force that is not 0? Well, in this case, you have to deal with the acceleration that will happen on that particular axis and operate with it normally. Okay, there is nothing substantially different in that case. The only difference is that previously, when you have things in equilibrium, all the forces in a certain axis, x or y, will add up to 0. In other words, all the forces pointing up have to be equal to the sum of all the forces pointing down, and all the forces pointing right have to be equal to the sum of all the forces pointing left. Now, at least in one of the axes, this is not going to happen. So either you have on the y-axis the sum of the forces pointing up being bigger than the sum of the forces pointing down, or the other way around, or on the x-axis, the sum of the forces pointing right being bigger than the sum of the forces pointing left, or the other way around. And if that happens, then you just have to equal in the corresponding axis the resultant force to ma. Okay, let's see. I use the example again of a car going up a ramp. And as you can see here by looking at the diagram, you can see that the driving force, represented here in orange, is much bigger than the horizontal component of the weight. So I hope that at this point you can just infer from the diagram that the car is accelerating upwards, right? Again, putting the referential as we usually do in ramps, x, y, you will know that in the y-axis, you still have the car in equilibrium. Again, you decompose the weight. That's the only one that you have to decompose. You have the FGY and the FGX. I already explained in previous lessons how big this is and how can you calculate it knowing the value of the weight and the value of theta, which is the inclination of the ramp. So assuming that you already know how to get the magnitude of these components, you will be able to see that on the y-axis, you still have the car in equilibrium. The normal contact force and the FGY, they are the same and opposite. Okay, so in the vertical component, you still have the situation that I explained in lesson 2. But in the horizontal component, this is not going to happen because you have the driving force much bigger than the horizontal component of the weight, which means that this is not going to be equal to this. In the vertical component, this equals that, but in the horizontal, this is bigger than that. So what happens in this case? You just equal it to ma. All right? Look at one thing, in case you missed it in the previous lesson. You are also doing this in the y-axis. You could have written this as n minus FGY equals ma. But you know that in a vertical component, the acceleration is 0, right? The car is not moving on the vertical component. So we speed up that process, and knowing that, we just equal this to that, okay? We are still applying Newton's second law over here, but since we know beforehand that the object is not moving in this particular axis, I just equal the sum of the forces pointing up, which in this case is just 1, to the sum of the forces pointing down, which in this case is just 1. Makes sense? It's still Newton's second law, but in a situation where the acceleration is 0, right? That's not the case in the x-axis, so you just write it as it is. The resultant force on the x-axis equals the mass of the object, which is the mass of the car, times the acceleration, right? So the driving force equals the FGX, which you already know is mg sine of theta, which equals the mass of the car times the acceleration. All right? Here is balanced, here is not balanced. One is not balanced, just equal to ma. And that is the only substantial difference between what you've learned in a previous lesson and this one.